This lesson is on differentiability, and we've actually already talked about that a little bit. If you remember, differentiability is the ability to take the derivative of something, and so that is something that we have to look at algebraically and graphically. So we're going to kind of focus on the graphically part again today. Just as a reminder, a function is not differentiable if, at that point, if it has a sharp corner, or a vertical tangent, or is not continuous. And remember that not continuous includes things like holes, jumps, and vertical asymptotes. So those are problems all that fall in this category. And so this question, where is f differentiable? A lot of times people don't read the question and they jump to the fact that, or they look for all the problems. Obviously, we've got a vertical asymptote at -2, so -2 is a problem. You have a sharp cusp at -1, that's a problem. One that some people don't notice sometimes because they're like, oh, it's continuous. But this vertical section at 0 would not be a differentiable place because if you did a tangent line, it would have an undefined slope. And then at 2, we've got a hole, and it's actually a sharp corner as well, so it's got a couple problems going on. Those are all the problems, but the question is, where is it differentiable? So that would be in the intervals between those places. So it's okay from -infinity to -2, but not including -2, so round bracket. And then from -2 to 1, or excuse me, -1, it's good. So between those two. Between -1 and 0, it's good. And between 0 and 2, it's good. And after 2, it's good. So it is differentiable in all of these places. It's just not differentiable at those 4 points that have the problems. Sometimes they'll ask the question, where is it not differentiable and why? Sometimes they ask the question, where is it differentiable? So make sure you read and are able to answer with the correct version of the answer. Okay, now we want to talk about some functions that you know the shape of and where are they not differentiable. So where do they have a problem? The first one is absolute value of x, and you guys should know that shape from your toolbox functions. Where does it have a problem? At 0. At x equals 0, absolute value has a sharp corner because it's that V-shaped graph, and that bottom of that V is at 0. Now, you also have learned about shifts of graphs, so if it's shifted right or left, you can figure out where that would be and where that problem would be. Okay, what about x to the 1/3? Where would the problem be there? It would also be at 0 because the x to the 1/3 graph is the inverse of x cubed, and when you turn the x cubed graph sideways, the part that had a horizontal tangent line on x cubed now has a vertical tangent line right here, and that is at 0. So it has that vertical tangent line right here at 0, and that's a problem. It's just for 1 point, but we have to think like that. C, I have taken that same graph, and which way have I shifted it? Right 2. So if I shift this graph right 2, where is my problem going to be? My problem is now going to be at 2. So my vertical tangent line would be now at 2. Okay, what about the square root of x? This is also one of the toolbox functions you're supposed to know. It's not in the negatives. Remember that this graph is like half of a parabola turned sideways. Where would the problem be? It would also be at 0. Because, again, this is the inverse of an x squared graph, and if you think about a parabola, an x squared graph, at the 0 on it, you have a horizontal tangent line. So if you turn that sideways, you now have a vertical tangent line. And so that problem is at 0, not differentiable right there. Okay, now we're going to talk about piecewise functions, and I've got us a simple one here, and so let's consider the graph of this. First of all, we have the graph of x plus 1, so that's a y-intercept of 1 and a slope of 1, and so that looks like this, but we want to only use the part that comes before 1. So close circle and finish that part of the line out. And it disappeared, of course. And then the other one has a slope of 3 and a y-intercept of -1. So but I only want the part to the right of 1. So if from -1 I go up 3 and over 1, I do hit that point, but then up 3 and over 1 again is a steeper slope. And so I haven't drawn this great, but again, think of going from a slope of 1 to a slope of 3. And it's not as clear on a hand-drawn graph unless you've got some graph paper and are taking your time, but this does create a sharp corner here at the place where they meet. So a sharp corner at x equals 1. Because these are two lines with two different slopes and it's an immediate change from one slope to the other, that will make a nice sharp corner if you can draw it correctly. Okay, so with that in mind, when you think about a piecewise function, if it's differentiable where they meet, then their derivatives are going to be equal at that point. The slopes coming in and going out will be equal so that it's a smooth transition. Now, it doesn't have to be always lines like these, but again, the slopes coming in have to match. So even if it's not a line, their derivatives are going to be equal because the slopes there should be equal if it's differentiable. Now we have a really important theorem that I did put in bold because this one does come up and you will have to use it sometimes as a reasoning, possibly on the AP exam. And it is, if a function is differentiable at a point, then it's continuous at that point. And so I really don't always add that point in. I just think if it's differentiable, then it's continuous. And it doesn't work backwards. The one we just did is a prime example of that. The one we just did was continuous, but it was not differentiable. But if you know that something is differentiable, then you know that it's continuous for sure. Because if the slopes are meeting, then it has to match up. It has to be connected. So if it's differentiable, then it is continuous. All right. And so I forgot to finish typing here, but my question was, is this function here differentiable at x equals 2? So the question is this function differentiable at x equals 2? And so what we have to do here is test just what I was talking about and see if their derivatives are the same. And so I want to take the derivative of the first one, which would be 2x plus 3, take the derivative of the second one, which is x squared plus 3, and then I want to plug the 2 in. So if I plug in 2, 2 times 2 is 4, plus 3 is 7, and then if I plug in the 2 at the bottom, 2 squared, plus 3 is also 7. Now what that means is the slopes coming in from one side are 7 and the slopes coming out of the other side are 7. But my next question is, that could happen and it could be a jump. Okay, so do these meet at 2? Do these two graphs meet at 2? How do you know that? You know by plugging in the 2. So 2 squared plus 3 times 2 would be 4, plus 6 is 10. and then 1/3 times 2 cubed plus 3 times 2 minus 1, so that will be 5 plus 8/3. And that's obviously not 10. Okay, so what does that mean? Now, we were testing if it's differentiable by doing the derivatives, and we said if it's differentiable then it's continuous, but the question was, I guess we should have started with the fact, is it continuous in the beginning? And no, this has a jump, 15, 16, so this is 23/3. This jumps from a y value of 10 to a y value of 23/3, although it does have the same slopes. And so it's coming in at 2 on one side with a slope of 7. Like we'll say that's a slope of 7. And it hits a y value of 10. And then on the other side at 23/3, it hits a y value of 23/3, but it also has a slope of 7. So it's a jump in the graph, and had I realized that to begin with, we wouldn't have done the differentiability. So this has a jump at 2, and therefore it's not continuous, and therefore it's not differentiable. We wouldn't have had to do this work. So the lesson to be learned here is, first, check and see if something is continuous. Because if it has a jump or a vertical asymptote or a hole, it's not going to be differentiable there. So don't just always jump into taking the derivatives and plugging in. Check the continuity first. And so for piecewise functions, if we're checking if it's continuous, you want to plug x into both equations. If you're checking if it's differentiable, you want to plug x into both derivatives. But let's put a little star right here and say check continuity first. And the only time you wouldn't have to check that is if they told you it was continuous. Sometimes they will tell you things like that. But if the graph has a hole or the graph has a jump, then it's not differentiable there, and you're wasting your time doing work just like we did. So good lesson learned, but this is kind of the math that you're going to be doing today. And that concludes this lesson.